and welcome to the chapter Ideal Flow Models. Now we are going to discuss the different flow models that are relevant for batch and continuous manufacturing. It is important to understand how the material flow behaves in the different manufacturing units and the fundamentals behind these flow regimes. We basically differentiate between batch and continuous flow models. In batch processes, the flow is intermittent, meaning that equipment is used for processing, much like a pot when you cook pasta, for example. You boil the water, add the pasta, wait until it's finished, and then you empty it in a sieve. Afterwards, you eat it, of course. So while in continuous processes, the flow through the equipment is constant, meaning that you have a mass flow going in and a mass flow going out, all out through the process. The processes that we will discuss now are so-called ideal processes, which means that we assume behavior in the equipment that in reality will appear a little different. I will point out these assumptions for the equipment so that you are aware of them and understand what the difference between this equipment and the reality is. First, let me provide you with an overview of the different types of reactors that we are going to discuss. Let's start with the batch processes. The most important batch process is the stir tank reactor. This type of reactor is typically depicted as a liquid-filled reactor. But the concept is also the same if it is a reactor for powder processing. The second type of batch reactor is the semi-continuous batch reactor. The continuous processes that we are going to discuss are firstly the plug flow reactor, then the continuous stir tank, and finally the continuous stir tank cascade. Now let's start with the batch reactor. What you see here is a liquid-filled reactor. You have a process vessel, which consists of the vessel, maybe a heating or cooling jacket, or a stirrer or a similar mixing device, like a screw. The process starts with filling of the equipment. Usually you have a minimum and a maximum fill level that provides good process performance. Depending on the process equipment, this range can be quite narrow actually. For example, a minimum of 60% fill level up to 100%. For other processes, when they are really expensive to run, like the freeze-drying process, it is not economic at all to run the equipment with anything below 100% fill level. Once you have filled the equipment, you start the process. This can take between several hours, up to days, or only a few minutes. This strongly depends on the kind of process. Examples are powder mixing processes for, let's say, 30 minutes, or a liquid mixing process for several minutes, or a drying process that lasts for some hours or up to days, just to name a few. After the process is finished, or perhaps it is better to say after the estimated process time has ended, you empty the equipment. In many pharmaceutical batch operations, now would be the time to check the quality of the material. This means that after the process has finished, you check if you have really achieved material in the quality you desired. If not, as there are no control actions that you can set, you could only process again or improve next time, which means you have to discard this batch. Obviously, I over-exaggerate here a little, because there are many process parameters that you control and check during the process. Stirrer speed, the temperature of the wall and the medium, etc. But you usually do that based on a process development on trial and error that you carried out earlier, rather than on process understanding. Our next process is the semi-continuous operation. Basically, this is also a batch operation, but is fully automated. In pharmaceutical operation, this can also be called micro-batch production. What does fully automated mean? It means that you still have your process vessel and the process steps of filling, processing and emptying, but you carry them out without manual intervention. The process is pre-programmed and could run completely autonomous and continuously creating many micro-batches. In addition to the vessel, now you also have, as you can see here, controlled valves as part of the process. Let's look at the process in detail now. First, Again, you fill the reactor, during which time the inlet valve opens while the outlet valve is closed. You have an online measurement instrument installed that controls the degree of filling. For this, different technologies are available. For example, to measure flow in the inlet pipe, or weight measurement of the vessel, or fill level measurement in the vessel. Once the filling is finished, the automated valve closes again. Now the process starts and the material is processed for a predetermined process time. Usually, these processes are time-based, so at the end, the processing stops and the emptying sequence is started. For the emptying, the outlet valve is opened again and the material flows out or is pumped out. Sometimes during the emptying, the steerer is also turned on at a slow speed to assist the material to flow out. The drawings I depicted here are just very rudimentary. To give you an idea, the outlet can also be at the bottom of the reactor, or it could be at an angle, or there could be an additional outlet for vapors or gases. But nonetheless, the concept remains the same. Now the really interesting part of this semi-continuous batch process starts. This process repeats itself again, fully automated, and it does so continuously, without manual intervention. Even though it is still a batch process, it is easily to recognize that this has many advantages. You drastically reduce the human interaction, and with that also the risk of exposure of both the product and the operator. With that, I would now like to move to the first truly continuous operation. What I'm showing now is an ideal process. As I have mentioned before, to understand rudimentary flow patterns in continuous flow, we first have to learn the ideal flow types, which build the basis for later when we discuss real flow behavior. The first one is the plug flow reactor. A volume flow rate indicated by a small v with a dot on top, or a mass flow rate indicated by a small m with a dot on top, is flowing constantly through the reactor. Thereby, everything that enters the reactor also leaves it. The volume might actually change as the density of the material changes with temperature, etc. But mass going in and mass going out is constant. In the animation, you see a small block flowing through the reactor. The reason for this is that in this reactor, we assume that no mixing takes place. This means that if you imagine a cluster of molecules that enter the reactor at the same time, they will stay all together in the same configuration until they leave the reactor, also at the same time. This is an assumption we make for this reactor. You are right to think that in reality, this will never be the case. You will have wall friction, meaning that even in an ideal laminar flow, you have a speed distribution along the diameter of the tube, and therefore your package will not stay together. Nonetheless, the consideration of plug flow is an important concept for continuous manufacturing, and you will hear wording like close to plug flow very often in this field. So remember, plug flow means a plug of material that enters the reactor, stays together all the time, that is in the reactor, and also leaves it together. This goes on continuously, so all material leaves in the same order as it came in, much like cars going through a tunnel on the highway, all at the same speed. So your neighbors are still your neighbors when you leave the tunnel. And as you know, with highways, there is an endless stream of cars. The unit we use to quantify this process is always mass flow rate or volumetric flow rate. Thinking back to the batch, we were talking about 100-liter tanks, 500-liter tanks. Now we are talking about the flow rate of 20 liters per minute or 15 kilograms per hour that passes through the reactor. The volume of the reactor itself is not the center of attention anymore. The next ideal flow reactor is the continuous stirred tank reactor. Much like the plug flow reactor, there is a continuous flow of material going in and going out, and the mass flow going in and going out is the same. The ideal stirred tank consists of a tank and a stirrer, so a rather easy setup. In contrast to the plug flow, we have the opposite assumption. Rather than the materials staying together, we now assume perfect mixing. You can imagine it like that. If you add a drop of red dye at the inlet, the color is equally distributed in the whole reactor at once without any delay. This means that we consider the concentration of the red dye to be the same in the complete reactor. Any change of concentration at the inlet would also result in an immediate change of concentration at the outlet of the reactor. You are once more correct with the assumption that in reality things are not as simple, black and white, no mixing at all or perfect mixing. Reality is more like a gray area, or sometimes even with blue sprinkles, so something completely unexpected. We will talk more about that later in the course. Now let's move forward to the next flow type. The continuous stir tank cascade consists of a series of continuous stir tanks. In theory, this can be up to an infinite number of tanks. For the tanks, we assume that the complete volume of all the tanks is the same volume as it was before for just one tank. This means that with an increasing number of tanks, the volume of the individual tanks grows smaller. You see where this is going. An infinite number of tanks means an infinitely small volume of the individual tank. Once more, not quite the reality, but you will see in the next chapter that with these three concepts for continuous production, we are already able to form models for reality in a way which fits quite well. With that, I'd like to thank you for your attention. See you soon with more details about continuous flow concepts.